Okay, so homogeneous catalysts. Still Maxwell-Boltzmann distribution exactly the same, regardless of whether it's a homogeneous or heterogeneous catalyst. It provides an alternative pathway with lower activation energy. So we can see that the area under the curve is greater in our Maxwell-Boltzmann distribution, and therefore a higher number of particles collide with an energy greater than or equal to the activation energy, and so react together exactly the same as before. But this is different. So whereas with our heterogeneous catalyst, it just had the same curve but lower, a homogeneous catalyst forms this intermediate. So you've actually got transition states either side, but you can actually isolate an intermediate. And in this example, which we're going to focus on in a minute, we're going to look at S2O8 peroxide disulfate ions and iodide ions. Okay, so definition hopefully you've got. So catalysts in the same phase as the reactants, quite often just all aqueous. There aren't loads of homogeneous catalysts that are in other phases. And the stages are slightly different. So to start with, the reactant and the catalyst react together to form an intermediate, and you might get a product formed in that first reaction as well. And then you get a second part of the reaction where the intermediate that's just been made will react with the other reactant to regenerate the catalyst and to form the product. And transition metal ions are particularly good for this because they can change oxidation state, and so you get two redox reactions, and in the first one maybe the catalyst might be oxidized and then it's reduced again, or the catalyst might be reduced and then oxidized again. Either way, the reaction, the different pathway has a lower activation energy, so the rate is quicker. I'm going to get you to pause the video in a second to look at this particular catalysis. Notice though, as you start, you've got two negative ions reacting together, and that's going to cause the activation energy to be very high because they just repel each other. And that's why the Fe2 plus catalyst is useful in this case. Pause the video and have a go at this task. And when you've done it, move on to the next bit and I'll go through some answers. Okay, before we go to the actual questions, I want to just show you that this reaction is thermodynamically feasible. We've already said that we've got two negatively charged ions reacting together, and that's going to give the reaction a very high activation energy because they repel each other. So it's not going to be kinetically feasible, but if it's going to happen with even with a catalyst, it must be thermodynamically feasible. So let's have a quick look. So we've got 2I minus over here reacting with the S2O8 2 minus. I'm going to identify where they are to start with, and that just means that I would be using these two standard electrode potentials. And if it's feasible, then we know that we need to get a positive E cell. Okay, so I look at these two, and this one is the more positive. This one's the less positive, so it'd be effectively the negative electrode. And we know that you get oxidation at the negative electrode and you get reduction at the positive electrode, which is what we want. So we want the S2O8 2 minus to go in this direction for it to gain electrons to become the sulfate ions. And we want the iodide ions to be oxidized to lose electrons to become I2. So it looks like it's going to work here. I could work out the E cell just to prove it. So E cell is going to be E of the reduction minus E of the oxidation, so 2.01 minus 0.54. And we can see that's going to give us a large positive value, so that's going to happen. Let's now go on to the question. I'll just get rid of these markings, they're not very helpful. So our question was, how does the ion 2 plus react with the S2O8 2 minus ions? So we'll do the same thing that we just did, S2O8 2 minus Fe2 plus. So now I'm using these top two standard electrode potentials. And again, I look at them relative to each other. So this one is the positive one, so that must be reduction. This one is the less positive, i.e. the negative one. So there's oxidation. And again, that's going to make sense. So we want the S2O8 to be 2- to be reduced. We want the Fe2+ to be oxidized. So that's going to happen. And I can work out E cell in a second, but this is going to make sense, and we're going to form one of the products in this first stage, and then we're also going to form Fe3+, which is an intermediate. So think back to what we said about homogeneous catalysts and how you form an intermediate in an in-between stage. Okay, let's do the E cell first, then we'll do the equation. So E cell, E reduction minus E oxidation, 2.01 minus 0.77 gives us 1.24 volts. So positive value. Let's do combine our two half equations. That's what we've got here. I'm going to multiply this by 2 because I need to have the electron transfer the same. So the electrons cancel. So now I'm multiplying that by 2. I must be starting with 2 Fe2+. I must be forming 2 Fe3+. And I'm going this side, so I've got 2 S2O8, 2-, and forming 2 SO4, 2-. So that's my first stage of the reaction. Sorry, it's a bit messy. And always worth just checking the charges to make sure that the charges are balanced as well as the atoms. So +4 -2, +2 on this side. We've got +6 -4, so +2 on that side. So that's all balanced up. Second question then. So we've made Fe3+ now. How does the Fe3+, the intermediate, react with the I-, the second product, the second reactant? So now we're looking at these two standard electrode potentials. That is the positive one, the more positive one, so that's our reduction. That's the more negative one, the less positive one, so that's oxidation. That's again what we want to happen, so the iodide ions are oxidized to I2. The Fe3+ is reduced to Fe2+. E cell, E right minus E left, so 0.77 minus 0.54. What's that? 0. plus 0.23. Okay, so feasible, thermodynamically feasible. And equation, again, I need to multiply this by 2 to get the electrons to balance. So I've got 2 Fe3+, this time becoming 2 Fe2+, and I've got 2 I-, becoming I2. And again, check the charges. So I've got +4 on this side. +6 - 2 is also +4 on this side. So I know that that's also right. So there's my second equation. So we've now got our two stages. And I just want to point out a couple of things to you. So we've got an intermediate, our Fe3+. We've got our products, just one of them produced in stage 1, one of them produced in stage 2. And we can see straight away, we start off with our 2 Fe2+ over here. That's our catalyst. It comes out, it's regenerated over here. So straight away, I'm showing that my catalyst is regenerated. So that's proof that it is a catalyst. And the question asks us to write an overall equation for the reaction. And the easiest way to combine two equations is just to add up the reactants and then add up the products together. So effectively a big sum. So I've got S2O8 2- plus 2 Fe2+ plus, now I'm adding up the reactants of stage 2, Fe3+ plus 2 I- goes to, now I add up the products, so products of stage 1, so for 2- plus 2 Fe3+ plus I2, so products of stage 2 plus 2 Fe2+. Okay, and we're ready to work out what cancels. So a couple of things we can see do. So our intermediate, our Fe3+, cancels, as does our catalyst, our Fe2+, and so our final equation is what we've got at the top here. So S2O8 2- plus 2I- goes to 2SO4 2- plus I2. There we go. So exactly the same as I've got up here, which is what you would expect. So overall equation shown. I've shown that the catalyst is regenerated because I've got it going in stage 1, coming out in stage 2. We can also see from here how this path is lower activation energy, because look at the charges. In stage 1, we've got a negatively charged ion reacting with a positively charged ion. Stage 2, we've got a positively charged ion reacting with a negatively charged ion, and therefore we've never got these two negative ions reacting directly together. So that is how homogeneous catalysis works.